Mean radiant temperature and comfort. With respect to thermal comfort, what might be surprising to you is that air temperature by itself isn't actually a very good indicator of how comfortable we are in a space. Thermal comfort is an absolutely fascinating field of study. Our comfort is based on a lot of things, including the temperature of the air, the temperature of the surfaces around us, the relative humidity, whether the air is still or moving, and how fast it's moving, if it's moving, how we're dressed, and what we're doing. You'll note that the thermostat setting is an indicator of only one of those things on that list, the air temperature. It might be helpful to point out that the air temperature in a space is usually a function of the design and operation of the mechanical system. What I'd like to talk about now, though, is the contribution of the building enclosure itself to thermal comfort. And to understand that, we need to know a little bit about mean radiant temperature. Imagine being inside on a cold winter day when it's 20 degrees outside. Imagine standing next to a large window. And imagine that it's either a cloudy day or that the sun happens to be on the other side of the building. The air temperature inside might be a perfectly pleasant 72 degrees. But if it's cold outside and the surface of the glass is cold, you will feel chilled standing next to that window. The reason is because our bodies experience radiant losses or radiant gains depending on the temperature of the surfaces around us. This is a really big deal when it comes to mechanical conditioning, comfort, and energy efficiency. Most people assume that well-insulated houses are energy efficient because the insulation prevents energy transfer across the wall or the roof or whatever element we're talking about. And that's true. But a compounding factor is that when the surfaces around a person are warm, they don't need the air temperature to be as warm for them to still feel comfortable. For example, suppose you live in a poorly insulated house and you set your thermostat to, 77 or 78 degrees in order to be warm enough in winter. And then suppose you were to retrofit the house, adding exterior insulation. You certainly can expect, post-retrofit, to save money and energy to maintain that same 78 degree interior temperature. But you probably won't actually keep your thermostat at 78 after insulating. You might only need to set the thermostat to 73 or 74 degrees to be comfortable. And actually, you'll probably be a lot more comfortable even at a lower air temperature. For the type of buildings we build and the place we build them in, North America, this effect tends to be more relevant to us in cold climates and in winter than in hot climates. Usually what's making us feel uncomfortable are radiant losses to cold surfaces, not radiant gains from hot surfaces. This is because our bodies are already pretty warm. Our skin is between about 92 and 98 degrees Fahrenheit. For us to feel uncomfortably hot from radiation, we have to be standing near or on something really hot, like a black asphalt parking lot in full sun. Sun shining on a large window can make the glass pretty hot, but the inside of our walls, even in a hot climate, never really get all that hot compared to our body temperature, which again is already hot. But the temperature difference between our bodies and the surfaces around us, the floor, the walls, that kind of stuff, in cold climates, in winter is much more extreme. That delta is just bigger. Most of the time, when we're thinking of non-mechanical ways of controlling the interior environment, we're talking about natural ventilation. But moderating the temperature of the surfaces around occupants by designing a well-insulated enclosure is also a non-mechanical or passive way of controlling the interior environment. Let's now introduce this concept of surface temperature and comfort to the design of typical walls. Now, obviously, not insulating our walls at all or by using lots of low performance glazing systems will have an effect on the surface temperatures around building occupants. But what about standard cavity insulated stud walls? Well, not surprisingly, it depends on how those walls are made. Specifically, the framing material matters and the spacing of that framing matters. If we're insulating our walls in between steel studs, our occupants are going to be a lot less comfortable than if we're using wood studs. This is because steel is conductive. We cook with it on purpose, specifically because it is conductive. What this means is that thermal bridging will cause the temperature of our interior drywall to be lower wherever there's a steel stud behind it. So the field of the wall between the studs might be relatively warm, but we have these stripes of cold at each stud. And this will cause us to be less comfortable, even if on average the temperature is just fine. This effect will occur with wood studs too, but in my view, the thermal bridging effect with wood studs is often exaggerated in discussions of both comfort and energy. Wood studs are about R4, which is a lot less than the R21 cavity insulation between the studs, but R4 is better than most windows, including a lot of high-performance glazing systems. This is a chart showing the reduction in overall thermal performance of a wall framed with either steel or wood studs, depending on the spacing and the amount of cavity insulation. You can see that the reduction in performance is fairly minimal with wood studs, but absolutely shocking with steel studs. Now, this is average thermal performance. This isn't showing surface temperature and it's not showing comfort. But the moderate reduction we see in wood studs and my own experience in wood-framed buildings that are otherwise well designed, as in they're airtight with good glazing, suggests to me that the effect of thermal bridging through wood studs isn't strongly connected to occupant discomfort, certainly not the way steel studs are. That said, my preference is always to provide exterior insulation outboard of the sheathing, and it's my preference for energy, for condensation control, and thermal comfort. And all of these factors are, of course, more significant when we're building with more conductive materials. Before concluding, I'd like to point out that the chart I showed you demonstrating the reduction in thermal performance is actually likely to be a little bit conservative. It was based on test walls that were built exactly as described, 2x4 at 16 inches on center and so on. Stuff like this was not taken into account. Or this, or even the typically poor installation of fiberglass batt cavity insulation. Continuous exterior insulation takes the edge off of all of these things. Minimizing thermal bridging really does improve occupant comfort, and it also provides energy, condensation control, and acoustic benefits. So if you were looking for another reason to love exterior insulation, here it is.